I know, they walk in late, it's all good. All right, so today we'll go over the homework first. And then we'll review. And then we'll eat jalapeno poppers, or you can eat them while I'm reviewing, I don't care. If you've never had them, they're not as hot as they sound. I tend to overcook them.
Did you make them?
Oh, yeah, I make them.
Oh, that's
Yeah, it's my thing.
used to the same question.
Oh, no, I make them. If you cook them extra long, it takes the heat out of them. But the bottom ones have jalapeno cream cheese, so they're hotter. The top ones are garlic and whatever. Anyway. All right, we can make that go away. All right, let's do the homework. 17 and 18. Right? Am I right?
Yeah.
Okay, perfect. 17 says reservoir discharge 4-inch new cast iron pipe. I grabbed the roughness. Find the velocity of discharge, consider friction, but neglect minor velocities. So we are to consider friction. We want the velocity here at the discharge. Yeah. So let's write the formula. Pressure goes away, right? For the input side. Velocity goes away for the input side, so we're just left with the elevation at the input. And then we need the elevation at the exit. What else do we need?
The velocity.
Velocity formula, V squared over 2G. No pressure, right? Because we're at the exit. Yep. What else?
The friction.
Yeah, the friction formula, which is F. Put it nice and light. And what's on top?
L.
The length, did they give us a length? How much?
175.
Thanks. 175 feet?
Yeah.
Okay. What else is on?
Scored.
Velocity squared on top.
Diameter.
Diameter down below, and do we want that in inches?
We want that in feet.
We want that in feet. 4/12,
2G.
2 and 32.2, right? Two unknowns. That should trigger something. What do we do? Right? Do we know this? No. How do we get it?
Thing.
Oh, damn it.
It's back on.
Good question. Is it trial and error? Huh?
My preferred method.
Trial and error.
Yeah.
Going back to statics. Or strengths. I don't even know where it got developed.
I think that was statics.
I think it was statics too. Yeah, so what do we put in for the friction?
0.02.
0.2, yep. So you plot that in. So here's the trigger, right? Two unknowns. We don't know the friction. We don't know the velocity. So when you have these two unknowns, then you go with trial and error. Put in the 0.02, come up with the velocity, go to the Moody diagram, check the friction factor. If it matches perfectly, you're done. If it doesn't, it usually doesn't on the first trial, then you go back through. You're supposed to continue to trial it until it matches. All right. So since you all have worked this, maybe some of you have, what do we get for V2?
12.133.
Did you get one? About the same? Okay.
1 feet back.
Okay. Probably just rounding then, so that's great. Feet per second?
Yes.
All right. Then we go to the Moody diagram. Yeah?
Yeah.
Yep, and we need two things. We need the
number.
Reynolds number and the relative roughness. So Reynolds number D V over viscosity. So 4/12 velocity 12.133. And then the viscosity of water 1 times 10⁻⁵. What'd you get for a Reynolds number?
0.0443333 times 10⁵.
4.044 times 10⁵. It's good. It's good, good. And then we need the relative roughness, which is our roughness, 0.00085 over the diameter. 4/12. Two zeros and 2 5. Yeah. Good morning. What's, Patrick, you're just pretty happy. What's going on?
I told Grace that I'm gonna be a little bit late, but don't worry, we'll get there right as right. Just talking about the relative roughness when we walked in.
That's pretty funny. So, do you guys think the potluck's today or next Monday?
We freaked out for like 2 minutes.
Dude, I freaked out.
And then we checked our calendar.
Okay, well, I thought it was today, but I think I put it on next Monday on the calendar, so. We're gonna do next Monday.
For here at the spot?
Yeah. I thought it was today, so I brought my snacks, they're back there, so we'll have those.
Class, you said it was this.
I think I did, but then I
thought it
went,
was happening.
but then I went and put in the calendar the wrong day, so there we go. It's all right, gives us all another chance to do it again. We can have jalapeno poppers today. And then we can have more snacks next Monday, and we can just keep having more snacks every day, so. All right. So from these two, we go to the Moody diagram. What'd you get for the friction factor from the Moody diagram? Or from the table if you went online?
0.02539.
0.02539.
2539.
02539. That must be from the table. Okay, does that match our 0.02? No, it's pretty damn close though, right? Pretty close. So it doesn't match though, so then we take it and we plug it back in up here and we go through the velocity again. What'd you get? Should be somewhere near this.
10.871.
Yeah, slowed it down a little bit, 10.871 feet per second. So then you would take that and you run it through again. Reynolds number would be dV over the viscosity.
3.624 times 10⁵.
And also get us a new relative roughness. What symbol do they give? Oh, they don't give that a symbol. Right? Same number.
The relative roughness constant.
Yeah, it's the same number. I was looking for it. Oh, it's right here. 0.00255. Then you take those two to the Moody. What'd you get?
0.02543.
So 0.025, 0.025. Say it's a match. Right.
Do you want us to double check it when we after like?
Yeah, after one run, you should at least check the friction factor and see that it's close. Like, that's within 4 places, so That's close enough for what we're gonna do. Yeah, so then that zooms and confirms that we have a velocity of 10.87 feet per second. Good. It's not so bad. You guys didn't like that the first time we did it. We thought that was terrible. It's not so bad.
the first time.
It's always bad the first time. Questions? You'll see one of these Wednesday.
You also have to get the discharge.
They want Q.
Yeah,
How do we get that?
area time velocity.
Yep. Q equals AV. So we're gonna take our area. This is in feet per second, so we need our area in feet. So maybe pi 4/12 over 4, that being the area.
0.087.
Sounds right. Times the velocity 10.87 feet per second squared. What we get for Q?
0.95.
Feet.
cube per second.
Yeah, so if the question was how fast will it fill up or how fast will it empty, something like that, that's always a Q, right? That's flow rate. So. Good. How big of a pipe? 4 inches. 4-inch pipe, right? That's like this big. So conceptually, I think it's good to wrap your head around that. 10.87 feet per second. That's like from here to the end of the table in 1 second, 1001. It's not super fast, right? And it's 4 inches. So we're not looking at that much of a flow rate. So about a cubic foot per second. How many gallons is in a cubic foot?
7 point something.
Yeah, 7.48. So every second we're pushing 7.4, you know, that's some flow. All right, good. Hi, Kevin. How are you? Good. 18. Says a reservoir discharges into a 10-foot diameter concrete pipe, 10 feet. It's huge. Freely at a point 2,250 feet from the reservoir. The elevation of the water is 825. The elevation of the invert, 695. Find the velocity and the discharge in the pipe. Consider friction, neglect minor losses. Same game, right? Same game. 825 here equals 695 plus V2 squared over 2G plus friction. What's on top? L?
LP.
2250. Is that V squared?
Yeah.
Yep. Don't forget to square it. Over diameter, 10 feet. And 2 and 32.2. Yeah. So not given the friction force, we are given the roughness. Because we know it's concrete and I think it said finished. So same game, trial and error. Put in your 0.02. And calculate a velocity. What'd we get for the 0.02 velocity? Everybody got it?
39.051.
38.2575.
Oh, crunch it. $16.1 for this one. Oh, I lost my number. What'd you get?
39.0151.
And then there was a second number.
I did it from the center of the pipe, so I just added 5 to split
Oh.
that 5. So it's 10-foot diameter.
Yeah, I think they want it from the invert,
Okay.
which is the bottom. I mean, that's gonna be the highest velocity down at the bottom. Or velocity a little bit higher. What was the decimal? 1?
0.0151.
0.01. Okay. Too much time. Now what? Yeah, same thing. Reynolds number. What'd you get?
3.9015. To the 10 to the 7.
And our roughness would be 0.001 divided by the diameter. Yeah. 10 feet. Then you go to Moody's. And you come up with a friction factor of somewhere near 0.02. Yep.
I got 0.12.
0.12.
Yeah.
Yeah, that one's fairly off. Compared to this. 0.2. All right, then we take it and we put it back here. And we come up with another velocity. This is really trial 2. Because now you have a new friction force. We should come up with something near this, 39. This is lower. Did it lower our velocity?
It increased my velocity, but because I had 700, it might be for H2, it might be a little different.
Oh, okay.
I got 46.64.
I got 47.52.
Yeah.
Okay. So then we run it again. Reynolds number,
752.
4.752 times 10 to the
7.
Our same relative roughness of 0.0001 gives us a friction force of
0.012. Again.
perfect. This confirms that our velocity is 47.52 feet per second. And then what's our Q?
The area times the velocity.
Yep. So area 10 foot, it's a big area. We should have a large flow rate here. 78.54 feet cubed per second.
Oh, no,
No, feet squared, feet squared.
Oh, that's the area? I was gonna say, I think it's bigger than that. All right, so I'll write this as area, and then it's gonna be times our velocity of 47.52. I'm saving my notes. Second, and we get Q at
3,732.21 CFS.
3,732.21
732.21 CFS.
CFS, cubic feet per second. Boom.
Big pipe.
Huge pipe. Yeah, 10 foot. Big, big, big. The tunnels in the Bonneville locks. So when I was with Kiewit, we built the Bonneville locks, the new lock. So we tunneled up to the reservoir part of the dam. Above the dam is the reservoir part, right? And then below the dam would be the river part. So you build tunnel systems that go up to the reservoir. So then when you want to fill the locks, you just shut the gate, open the tunnels, and it fills it. No pumping required. It's all gravity fed. And then when you want to lower a ship, then obviously you open lower tunnels and just let it out again. So again, no pumping. There's no pumping involved whatsoever in a lock. It's super cool. Those tunnels were 12 feet in diameter. And they can move the elevation of the locks from the top down 34 feet in about 2 minutes. So they can lower a ship in 2 minutes. It's crazy. But we had to build those tunnels. We had to drill them out. And yeah, we had to calculate some flow rates. That was kind of fun. All right. You want to keep them for the exam? Turn them in after the exam? Does that work? All right, so let's not forget to turn them in. I'll try to remind you. But you can keep them for the exam, so you have them ready to go. The potluck is gonna be Monday. I know, I mucked it up. It was supposed to be today. So I brought my snacks because I didn't know if I screwed it up or obviously I screwed it up. I was in charge of it. So clearly I screwed it up. So we'll do it again Monday. I'll bring a different snack on Monday. Okay. But today there's jalapeno poppers. If you want one. I know it's not really a breakfast food, but I love them, man. They're my favorite. They're in that green case back there. And I think we should take a break right now and have one. If you want one, no pressure. You don't have to have one. But the garlic ones are on top. No one's really.
What are they?
Jalapeno poppers.
You know what jalapeno poppers?
Oh,
I never had jalapeno
Especially if
poppers.
they're very spicy, no, I don't want that.
No.
It has cheese.
Cheese and jalapeno. So these top ones
I sound like I'm.
are the less hot.
Yeah, it's Vancouver.
These are less hot in.
Why would I ever live there?
These are the hotter ones because they have cream cheese.
No.
Aiden, you're gonna love it, man. It's gonna be your new favorite thing. Huh? You'll bring brownies? Dang, that's definitely good breakfast food. I love it. You don't have to bring something. It's just for fun, so.
Bring tacos.
Dude,
I'm gonna have a full buffet.
I know kidding, man. Maybe I'll invite it.
Was going to bring tacos. Taco Bell last week. So no, because I have years that I don't buy there. I was amazed how expensive they are right now. Oh my God.
They still
Alright, let's talk about the exam. I know, Wednesday. It's gonna go all the way back to chapter 2. So what did we do in the very beginning? Anyone remember?
Pressure.
Chapter.
Before pressure. I know, there was something before pressure. Properties of properties of fluids is what we did.
Final, right?
No, this is just exam 2. Yeah. So we did specific weight, I'll just call it,
Hydrostatic, right?
and we did density. And we did viscosity. So what was specific weight?
52.4. For water.
What's the unit of it? Specific weight is gonna be, no, when it says weight, it's pounds. That's your Q. Specific weight is pounds per volume. Right? So pounds per volume or weight per volume. So you might be asked to find the specific weight of something. That's the first little lab we did with those jars. Right? You weighed it, you calculated a volume, came up with a specific weight. Different than density. Density is what somebody said is mass per volume. So density, mass per volume, specific weight, pounds per volume. Viscosity is just the slipperiness, and that's just a constant for each different fluid. So water's the one we've used a lot. So obviously you're gonna probably have several water problems. So that was the very first thing we did, was this different properties of fluids.
Did we calculate viscosity or?
No, we did not calculate viscosity. Nah, it's done by experimentation, so we're just giving it, just know when to use it, how to use it type of thing.
What's your favorite?
Slag.
All right, then we went to the next chapter and we started with pressure. How do we calculate pressure?
Force divided by
Not force,
pressure.
pressure.
Yes.
It is force per unit area. That's the unit of pressure. But how do we calculate it? Like if we have a tank of water and we want to know the pressure at 20 feet. Yeah, so it's this, they call it Z times the specific weight. Yeah, just the depth times the specific weight of the fluid. So make sure you use the right units when you're calculating. So if you have different fluids, we need different, this is a fluid property right there, right? That's equal to pressure. And Jorge's right, it was feet squared pounds per feet squared or pounds per inch squared or newtons per meter squared. PSI, PSF can come to you anyway. So look for that on the exam. Might ask you for pressure in PSI. I might ask you for pressure in PSF. So just make sure your units are working well. If like you want to work an example problem of any of these things as we're going through it, we can do that in the end. Let's kind of go through the list of things.
At Newton per meter squared is a Pascal, right?
Yes, that's correct. Then we kept going with pressure, and what did we do next?
Hydrostatic force.
Hydrostatic force. So If we have a vertical surface underwater, we can ask what the hydrostatic force is on that surface, right? Remember, hydrostatic force works in all directions. Go ahead.
You're, I don't know if that's what you meant, pound per feet square, and then you put the PSI, that would be.
Oh.
PSI.
I just was, yeah, I was just writing.
PSS.
Yep. I like it though. Good. So we did vertical surfaces, we did horizontal surfaces, and we did a slope surface. So all these different surfaces would have hydrostatic pressure on them. So if it was a vertical surface out here, it's gonna have a lower pressure at the top, higher pressure at the bottom, and it's gonna make this kind of a pressure curve. Right? It's a force curve. But actually it acts all the way around it. Right? So if it was out here in the middle somewhere, you could calculate the hydrostatic force on either side. If it was vertical, it's going to be the same. Horizontal surfaces made a little different graph. And hydrostatic force is in pounds or newtons, right? So it's not a pressure. Hydrostatic force is the concentration of those distributions. So we did a fair bunch of those problems. So normally what we're going to be given is a flat surface at the bottom. We might want the hydrostatic force. Maybe that's a, some kind of gate valve that's going to be closed, or there's some kind of a gate that's vertical. That's the normal reason for calculating this hydrostatic force thing. To try and figure out how much force is on these surfaces.
0.
Not if they're here, not 0.
Oh, you mean surface? I thought that you
Yeah.
were talking on the upper.
Oh, no, the upper surface, there's not much, right?
That would depend on the depth.
Big time. Yep. Remember this? Okay, good. Then we went into. Yep. Buoyancy. We did buoyancy a couple different ways. One way to do buoyancy, like when we have an object underwater, right, or at the top surface, is to calculate the hydrostatic force. So that's one way to do it, right? Because as something is deeper and deeper in the water, it's going to generate hydrostatic force. Hydrostatic force is pushing up. The weight of the object is pushing down. If the weight of the object is less than the hydrostatic force, it's going to float. If the weight of the object is more than the hydrostatic force available, it's going to sink. Right?
Would it be accurate to say that it gets less buoyant as it sinks? Because the pressure.
Big
builds?
pressure increases and the weight of the object is the same. Yep. Things at really deep depths have very little weight to them.
You can use notes, right? This example.
Yep. Absolutely.
Open notes, open internet, open everything.
Not open everything.
What?
Not, I don't know. I don't know about internet. I don't think you'd need it unless you're gonna run the Moody diagram.
Yeah, I don't have the textbook, so
So-
I use it for the Moody diagram and then.
Yeah.
usually just use it for-
Mine will be available, so. Actually, I can make copies of the Moody too. Or put it on the test. All right, so how else do we do it? How else can you do buoyancy?
If the weight of the object, is lighter than the weight of the water.
Like the water being displaced.
Yep, displacement of water, yep. Both of you are spot on. So if you calculate the volume, right, of an object. Uh-oh. Oh, just showed up, maybe. Nope, it's gone. calculate the volume of the object. If it goes fully in the water, that would be the water displacement, right? That volume would displace that amount of water. You calculate that weight and compare it to the weight of the object. You can determine if something floats or doesn't float. This was the way to do it when we did water line. So to calculate the water line, you just set up that formula that is the volume of the object, right? And leave that height an unknown value and set it equal to that weight of the object, because it's got to displace that much water. So that's how we did water line. That was good. I think this is chapter 3. I think this is chapter 2. Chapter 1 is kind of an intro to fluids. We didn't do much in there. It's like mathematics and significant figures and the history of fluid mechanics. So then there was chapter 4, which we just completed. Right, and that was conservation of mass. And that's the A1V1, not Q. A1V1 equals A2V2. So that just means that that velocity and flow rate has to stay the same. The flow rate has to stay the same in a system. And then from that, we developed Q, A times V. We talked about Reynolds number. And then we talked about the Moody diagram. Right, and then the friction factor and the whole Bernoulli's equation. Which you just did a homework on the hardest type of Bernoulli's equation, so. You should be pretty set for that. What the mistake that gets made on this test is you do too much. I ask you just to find the flow rate in a system. I give you a big complicated system, and then somebody goes off on the Bernoulli's equation. It's like, you don't need to do that. If the velocity is given and the area is given, you just find the flow rate, right? So all the problems look complicated, but all the questions are not complicated. So don't just attack it with Bernoulli's every time. Just try to read it and really understand what you're trying to find, and then just give me that.
On the exam, is it open internet for like a Moody diagram?
Sure.
Later?
Yeah, sure, I'm okay with that. I make my own exams, so it's not like you're gonna go out and find these questions out on the internet, so I'm not really worried about it. I have a lot of questions to pull from that I've made over the years, so. All right, that's it. Piece of cake. All on one page.
Can you do like a example problem for hydrostatic force?
Yep,
For
let's do it.
vertical.
Well, let's do it.
I have a question about last week's.
Yep, I'm listening.
Lecture, where I'm looking for. Did you, record it?
One of them I didn't. I don't remember which one though.
Wednesday.
Wednesdays I missed.
Wednesday, Monday night, I did it.
It recorded to Mondays was holiday.
Oh, that's right.
Yeah. So it was just Wednesday, and then I think it recorded to the station and then it got wiped. I know.
Yeah, I couldn't, I wanted to review on Wednesday.
Yeah, no, I think it got wiped. Unfortunately. All right, so we'll say we have a 30-foot tank. And it's got an exit here. And this exit is gonna be 2 foot in diameter. So that 30 foot is not real clear. Here, we'll do this. Top elevation is 600 feet. Bottom elevation is 570 feet. 2-foot diameter, and there's a gate here. I'll make it more test-like, because I probably wouldn't give you a diameter. I'd give you a 2-foot square. 2 foot by 2 foot. Exit. Height.
It's a square tunnel?
Yep. And the question would be, determine hydrostatic force on gate. So to get hydrostatic force, we have to know what? We gotta know the depth, we got that. What else?
Fluid, oh no, gravitational.
Specific way to water, specific way to water.
We gotta know the specific way to water for sure.
The water,
So what acts on this? What's this thing called that's acting on the gate?
pressure.
Yeah. I didn't want to use the word, right? Pressure's on it. Right? So we have to know the pressure at the bottom of the gate. And we have to know the pressure at the top of the gate, because we would want to draw the pressure curve. I'll just blow the gate up out here. Pressure is going to be greater at the bottom, less at the top, but there's definitely pressure at the top. So it's going to create this kind of a curve, right? So this is the gate. It's 2 feet tall and 2 feet in depth. So we need this P2 and P1. How do we get that?
572, 570.
So the depth times the specific weight. Yep. So P1 equals 572, right? Or what?
Yeah.
Is that the right? What's this distance?
28.
Yeah. So 28 feet. Because it's 30 from here to here, right?
Yeah.
Yeah. So that's 30. And then what's the specific weight of water? 62.47 pounds per foot cubed. So that gives us P1. $17.49. Anyone else get that?
Yeah.
16 PSF. And then what's P2? Now we're 30 feet deep.
Then 71.1.
I get 1874 PSF.
Thirty times 62.47.
Yep. I get it again. Now what?
You say PSI, it's PSF.
I said well, I wrote PSF. Don't average it. How do we get hydrostatic pressure?
finding
We
the,
find the area.
We concentrate it, right? This is hydrostatic force. Is the concentration of this distribution. And this distribution goes all the way around this thing, right? Like it's a volume of distribution. So we have to find that volume. If it was just a rectangle, that's pretty easy to do. There's a couple ways you can do this. You can go look for the formula for this shape, or you can just break it into a triangle and a rectangle. I'd probably just break it into a triangle and a rectangle and find those two volumes, add them together, and you got the hydrostatic force.
Wait, is the volume or is the area of the?
It's the volume of this distribution. Yeah, it's the volume of it. So it's gonna be like if it was just this rectangle, that's P1, which is right here, times 2 feet times 2 feet. That's the volume of the rectangle. Agreed? Yeah. So that one's not too bad. Volume of the rectangle is 1749.16 pounds per foot squared times 2 feet times 2 feet. Right? Length times width times this depth thing. And all of the feets disappear and we're left with pounds, which is what we want. Hydrostatic force is pounds. So this is just to the rectangle. Six 996.64 pounds. Rectangle. Now we need to do the same thing for the triangle. So you have to subtract this from this to get the triangle. The triangle is right here. That's the base of the triangle. So that's not too tricky, but this is going to be P2 minus P1, right? That little pressure curve of the triangle. So that is the difference between these two, 1874.1. So this would be the volume of the triangle. It's going to be 124.94 pounds per foot squared times 2 feet times 2 feet.
Shouldn't there be a 1/2 in there since it's triangle?
Oh yeah, 1/2 the base times the height. Thank you. Thank you. That would be a big mistake. $249.88. So there's the rectangle, there's the triangle. You just add them together to get the total hydrostatic force. Seven two four six five two.
From the location, or is it just? it's just
So,
there?
well, if the problem said find the location, then you'd have to find the location of that shape.
Okay.
Yeah. I'd look that up. There'll be a formula for that location. Yeah. So if it just said find the hydrostatic force, then we'd be done. Good? That's a good one to remember how to do. What else? Buoyancy, I think you got it. This won't be too bad. There'll probably be 7 questions, 6 or 7, I would guess. So. Definitely a velocity question coming out of a reservoir. With friction or without friction, something like that. There'll be a buoyancy question. There'll be a hydrostatic force question.
Do hydrostatic force on slope.
I haven't written it yet, so I think we only did one of those. So the way I write an exam is I put on there what we spent the most time on. So we didn't spend a lot of time on sloped. We should definitely be able to do a vertical or horizontal surface for hydrostatic pressure.
We did do it on the slope. It's always perpendicular.
It's the same curve, right?
Yeah.
So on this slope right here, smaller pressure here. Right? Larger pressure here. We did not do curved surfaces, and that is in the book. So like a tank with like a curved gate on it. We didn't do that. You could do it. I know you could. So usually what I find is once we go through all of this, student can go to the book and grind out a curved surface if they absolutely have to. So not gonna be on the exam. Yep. You can come in earlier if you want more time, for sure.
You should put something crazy at the end for extra credit.
Okay, something crazy at the end for extra credit. I love it.
And then partial credit if we just don't get
And then
It's
just,
just a couple points. Just
how about just some crazy extra credit just for showing up? I think that'd be great.
it. On time.
So I'm usually here at 7. I mean, you don't need to come at 7, obviously, but I'm usually here at 7. So you can come early if you want extra time. Take the. Dude, exactly. Love it. It's cold out there today.
That I put in the freezer, I'm trying to keep up.
Back to food, man. We got the foodies going on in this class. I love it. All right, that's it. That's all I got. Game on Wednesday. I would come on time at least on Wednesday. We're in the habit of sliding in late, which I don't care. You can come late. But Wednesday would be a good day to be on time.
Okay, okay.
Yeah.